I will introduce the next speaker, Zahid Asghar from Mayvan Clinic, located in Brampton, Ontario, Canada. If you're here, the stage is yours.
For the introduction, I'll be sharing my screen now. Hope everyone is doing well today. So my topic for today is an in silico analysis of pentraxin 3 as a predictor of ethanol and morphine-induced inflammation. So to begin, I think the social impacts of both alcohol and opioids cannot be understated. In terms of acute intoxication, alcohol accounts for 178,000 deaths annually, and opioids account for 81,806 deaths as recently as 2022 in the United States. This is just in the acute intoxication. In terms of long-term systemic effects, they can lead to the pathogenic development of diseases such as fatty liver disease, hepatic encephalopathy, can lead to damage to CNS structures such as the brain, etc. This is by no means an exhaustive list of potential long-term side effects, but these are just some of the complications associated. They are some of the leading causes of preventable death. Sorry. Sorry, just having some technical difficulties. Okay. Sorry, I'm just having some technical difficulties.
No problem.
Okay. Okay. Okay, so like I mentioned, they are common cause of disease in both in the acute intoxication as well as chronic long-term disease, right? So in both the acute intoxication and the long-term systemic effects, inflammation is often a hallmark of disease. And in terms of inflammation, what typically happens is that immune cells such as macrophages, dendritic cells, neutrophils, etc., right, are recruited, and those immune cells then release inflammatory cytokines such as TNF alpha, IL-1, which then mediate their inflammatory effect via recruitment of other immune cells or via cellular cellulling, etc. Right? And in clinical practice, we have several modalities that can measure this level of inflammation. Two very commonly used clinical modalities are CRP and ESR. CRP stands for C-reactive protein, and ESR is erythrocyte sedimentation rate. And CRP is one of a few acute phase reactants, which are essentially regulators of inflammation. They are upregulated by certain inflammatory cytokines, such as TNF alpha, and are released by other inflammatory cells, such as macrophages, monocytes, including endothelial cells as well. And they are essentially regulators of inflammation. Their concentrations correlate with the degree of inflammation. Now, one such acute phase reactant is pentraxin 3, which is an APR, which is in the same class as a C-reactive protein. So they are both pentraxins. And in this study, essentially, we want to look at whether or not we can utilize pentraxin 3 as a predictor of ethanol and morphine-induced inflammation, as there is very limited literature in this regard. So our hypothesis is that pentraxin 3 will be upregulated when concentrations of ethanol and morphine are increased within macrophages, the brain, astrocytes, neurons, and other neuronal structures. So in terms of methods, we utilize the in silico method, IPA, Ingenuity Pathway Analysis from Kaizen, which basically allows one to sort of simulate biological processes, biological pathways. So firstly, the path explorer function was used to identify common biological pathways between ethanol, morphine, and pentraxin 3. And then the molecule activity predictor function was used to like either increase or decrease concentrations in the computer simulation to determine whether or not increased concentrations of ethanol or morphine will lead to a predicted activation or predicted inhibition of pentraxin 3. All right, so moving on to the results that we found from our analysis. Prior to moving on to that, I'd just like to show a legend of how the color scheme sort of works with the molecule activity predictor. If a molecule appears as red as this, it means that that molecule has been increased in measurements in concentration. The green color means that it's been decreased in measurements. However, this has not been utilized in this analysis. And the orange color right here denotes predicted activation of a downstream molecule. A blue color like this denotes predicted inhibition. So we'll move on to the analysis now. We started our analysis with macrophages. So to the left, we see here is ethanol being connected to pentraxin 3. And to the left here is showing the shortest paths. So essentially, the system shows you either the pathways that are in the shortest paths with the least number of intermediary nodes. In this case, there's this TLR4 connected to whatever molecule you are looking to analyze between. And in this case, in the shortest paths, you find that there is no predicted activity of pentraxin 3 after increasing measurements of ethanol. After including shortest path 1, which is one additional intermediary node connecting your two molecules together, we find that there's predicted inhibition of pentraxin 3. Additionally, I wanted to also analyze specifying for specific relationship types, namely activation, causation, correlation, expression, transcription, and seeing what effect that might have on the results. And there was a clear difference. There was far more intermediary nodes when we compare it to just, like all relationship types. When you specified for relationship types here, we saw far more intermediary nodes. So that was like just something interesting that I found in the analysis as well. So in both cases, when you look at shortest paths, we see here that it leads to predicted inhibition is a blue color right here, leads to predicted inhibition of pentraxin 3. And when we added shortest paths 1, we found that there was also predicted inhibition of pentraxin 3. For morphine, we found that in the shortest paths, there was predicted activation of pentraxin 3. And likewise, with shortest paths plus 1, there was also predicted activation of pentraxin 3. When looking at our specified relationship types, activation, causation, etc., in the shortest paths, we found that there was predicted activation of pentraxin 3. And with shortest paths plus 1, the additional intermediary node, same thing, predicted activation. And then I also wanted to analyze both of them combined. So morphine plus ethanol, their combined effect on pentraxin 3. We found in the case of shortest paths, there was predicted activation. In the case of shortest paths plus 1, we found that there is also predicted activation, but to a lesser degree. And when we looked at the specific relationship types, activation, causation, etc., we find that ethanol and morphine in shortest paths does have a connection, does lead to predicted activation. However, ethanol does not share a connection. That's just how the algorithm made the connection there. And adding shortest paths 1 showed predicted activation of pentraxin 3 as well. So to summarize those results, in macrophages, we found that for our specified parameters, ethanol, for the most part, led to predicted inhibition. Morphine primarily led to predicted activation. And morphine plus ethanol led to predicted activation primarily as well, only with shortest path 1 here. And all relationship types, we found that there was a slight activation. And basically, SP stands for shortest paths. SP plus 1, shortest path 1, SR specific relationship types, those ones that I mentioned. And SR plus 1 is the specific relationship types, including the shortest paths in that as well. All right. And some of the neuronal structures that I looked at was the brain, for example, right? So in the brain, when I analyzed for ethanol, I found that in shortest paths, there was no predicted activity of pentraxin 3. However, when I added the shortest paths 1, there was predicted activation in pentraxin 3. For the specific relationship types, in shortest paths, I found no predicted activity. However, when I added shortest paths 1, there was predicted inhibition in pentraxin 3. And for morphine, there was no predicted activity in shortest paths 1. However, shortest paths did show predicted activation in pentraxin 3. And finally, morphine plus pentraxin 3 both together, we find that there's predicted activation in pentraxin 3 with shortest paths. Additionally, predicted activation with shortest paths 1. And likewise, when we look at what's it called? This right here is the specific relationships. This right here is the This is all the relationships. We see that for all the relationships, shortest paths shows no predicted activity, and shortest paths 1 shows predicted activation. Okay, so to summarize those results, We find that for ethanol, for some of the molecules, for some of our specifications rather, there was no predicted activity seen. However, in the shortest passless one, we found that there's predicted activation, slight predicted activation, and for the specific relations, there was a slight predicted inhibition. Morphine, there was predicted activation, and for the most part, ethanol plus morphine, there was no activity that was found. And I just went ahead and did the same analysis for the other neuronal structures I was looking at. I'm just going to summarize those results right now. So for microglia, specifically looking at microglia, which are the resident macrophages within the CNS, we found that ethanol produced no findings. Morphine had a sort of mixed result. The shortest paths for all of the relationships and also specific relationship types after selecting for those, we found that there was predicted activation. However, when we added shortest passless one, there was no activity seen, and the same could be said for ethanol plus morphine. It was the same results that we saw. And then for neurons, primarily for ethanol, there were no results produced, except for the specific relationship types and selecting for shortest passless one as well. On top of that, there was predicted inhibition. For morphine, there was slight predicted activity that was seen for shortest passless one, both for all relationship types and specific relations. And for ethanol, primarily, there was no predicted activity seen except for specific relationships that added shortest passless one. And then finally, I also looked at all the neural structures together to see what that overall effect would be showing after adding all the neural structures that I previously mentioned, the brain, microglia, neurons, etc. So for what I found interesting in this is that for ethanol, when there's only shortest paths, we find that there's predicted inhibition. However, when adding the shortest passless one, there is predicted activity, both for all relationship types and also the specific relationship types that were mentioned. And for ethanol and ethanol plus morphine, in both scenarios, we see predicted activation. So to summarize all of those results, we find that for the most part, ethanol sees either no activity seen or a general trend of predicted inhibition. In a couple of cases, such as in the brain, we see predicted activation. And for all neuronal structures, we see that when we add shortest passless one, in that scenario, we do see predicted activation. However, for the most part, uh, I don't think you can conclusively say that it did lead to predicted activation in pentraxin 3. However, morphine did show a general trend in predicted activation. And ethanol plus morphine was somewhat of a mix between the two. It produced some scenarios it did not produce results. However, in others it did produce results. And I've also gone ahead and just stratified the results in the different modalities that data was collected. So when we see it being stratified in terms of all relationship types and shortest paths, in this scenario, we see that ethanol primarily does not lead to any activity, none was available. Morphine does lead to predict activation, both for all relationship types and specific relations. And ethanol plus morphine, both of them combined lead to a sort of mixed result, you can say. And when we added shortest passless one, that additional intermediary node, we do see that in the case of ethanol, it does lead to more results as opposed to just shortest path. So, that's one thing to note. And ethanol plus morphine and morphine on its own produce, if not the same, just slightly less results as opposed to just the shortest paths. So in conclusion, we can say that increased measures of morphine activation, morphine do in fact activate pentraxin 3 in macrophages and these specified neural structures such as the brain, neurons, etc., right? The same cannot be said for ethanol, however. We cannot say that it led to the activation of pentraxin 3, more so it led to the inhibition of pentraxin 3. And it would warrant further analysis because there were a lot of cases where there was no predicted activity. And ethanol and morphine co-administration do not have any sort of synergistic effect in activating pentraxin 3. The initial thought was that maybe it has some sort of synergistic effect. However, that was not seen. In terms of next steps, I think it would be quite important to run a core analysis and to determine p-values, to determine statistical significance. In addition, performance of in vitro analysis on macrophage models, and then running a core analysis from that macrophage generated data from the in vitro study. And I would like to also acknowledge the valuable contributions of Dr. Muhammad Khan. His contributions were very valuable. And thank you for your time.